Well, well, well. Good morning, DiffyQs. So today we're going to do a screencast that would have been the lesson for the class today. For my section with Matthew, Ariel, Adam, etc., you're probably going to be able to fast forward the first 2 or 3 minutes here because the other class didn't get the very short, about 10-minute intro that we gave in class yesterday, okay? So I can't think of a more, I guess, interesting way to have a senior winter of a high school, having what, 5 cancellation days now, and this one due to power, which just is an incredibly twisted string of events, or a very elaborate senior prank. But I don't want to, sow the seeds of any kind of uprising among you all. Okay, so let's just remember what DiffyQs are. Differential equations, or DiffyQs, are nothing more than equations that involve derivatives. So really what we do here in this course is we go back to the world of calculus and we focus exclusively on differential equations. Really, you've been working with differential equations all through calculus. I mean, quite frankly, back in the day when you looked at something like this, and then you went and did this, what you did was you created a differential equation. And the first part of differential calculus was going in this direction. Then you hit the second part of calculus, or integral calculus, when you went in this direction. And so the course of differential equations will very much focus on going in this direction, which means taking a differential equation and solving it for either a general or a particular set of solutions, okay? Before we get into that, let's just make sure we understand some vocabulary. When you talk about DiffyQs, there's ways to classify them. DiffyQs are classified in terms of their order and in terms of their degree. When you classify a differential equation by its order, what you are looking at in the differential equation is essentially the highest derivative represented. Okay, and so, for example, if I gave you this equation here, dy dx plus 3xy squared minus or equals dy dx squared, for example, this DiffyQ here is of order 1. All right, it's of order 1 because the highest derivative you see here is the first derivative. This is the first derivative squared. If you are being very careless and looking at this, someone would say that this is an order 2. That would not be the case. The order is the highest derivative. This is the first derivative, okay? Similarly here, if you looked at, something like this, okay, this DiffyQ is of order 2. All right, so in terms of differential equations, you can classify them by kind of the highest derivative represented in the equation, not to be confused with the power of the derivative. Let's go to degree now. When you classify a DiffyQ by degree, what you want to think about here is the highest power represented, the highest power of the dependent variable or the dependent variable's derivative. So what I was about to write here was I was about to write the highest power represented of y, or the derivative of y. But the reason why I didn't is because, as you can imagine, your equation is not always going to be in terms of y and x. So the dependent variable won't always be y. So the degree of a DiffyQ is the highest power represented of the dependent variable or the dependent variable's derivative. So let's take a look at this DiffyQ over here. Okay, we know the order is 2. And let's take a look at the dependent variable. The dependent variable appears here, cos y. It also appears here. It also appears here. And the highest power of either y or dy dx is 2. So this DiffyQ here, right here, is order 2 and degree 2. Okay. Similarly, let's go over here now. Let's take a look at this. Okay, this differential equation is of degree what? That's correct. It's degree 2 because the highest power is right here. It's degree 2. That 3 here would tell you that the diffie-q is of order 3. All right, so that's the distinction between degree and order. You have to be careful. Sometimes you can be really tricky. I gave this an example that was similar to this yesterday. What about this one? Okay, what would you say the degree of this diffie-q is? I'll tell you what the single most common incorrect answer is. The most common incorrect answer is to scan this very quickly and say the degree of this diffie-q is 2 because your eyeball is looking right here at this power. But really, you have to be careful because if you look at this term right here, this dy dx, if I were to distribute, I would have 2 dy dx minus y squared dy dx plus xy equals dy dx. And what you see here is this term right here involves y squared times dy dx. So actually, this term is actually degree 3. Okay, because y is being raised to the second power, and then the derivative of y is being raised to the first power. This is a degree 3 diffie-q. So just be careful when you look. You want to look at the highest power represented of the dependent variable or the dependent variable's derivative, but be careful. Sometimes it's not going to be the most obvious. You have to just kind of step back and take a look at it in the case of something like this, where a single term could be a product of the dependent variable and a subsequent derivative. All right. The reason why we spend some time talking about classifications of diffie-q's by order and degree is because as we go through this course here, what's going to be very helpful to us as we kind of set up the kind of our menu of solving differential equations, sometimes the order and the degree will tell us or direct us towards a certain methodology. Okay. Now, I talked a bit about the fact that you've been working with differential equations for many months, and really, I think what you worked with differential equations last year was in the context of probably separation of variables, right? When you solved this differential equation, you probably used a method called separation of variables, which I'll review when we kind of need to review it. But I want you to also not forget that you also worked with differential equations that involved just the independent variable. So this here is a differential equation. One would argue it's a very easy differential equation because if I were to solve it here, I would get this solution. So let's just make sure we understand and remember some terminology. The solution to a differential equation, if you're not given a particular point on the solution to a diffie-q is a family of solutions. Okay, or it's a set of infinite solutions. And this family of solutions differ by some vertical translation C. If you were then told, for example, that dy dx equals x squared, and maybe you're told that y of 0 equals 6, right? What this point then allows you to do when you find the family of solutions is it allows you to solve for the particular constant C, in which case you can then slim down the family of solutions down to a unique or specific solution. Now, if you're curious, and here's where I think we'll pick up with all of you together now. So I'm seeing it's a little more than 2 minutes, but I tend to digress a little bit. If you're curious here, in our course of differential equations, because diffie-q's is, after all, a full standing course in college, it's also a full standing area of graduate study, because really differential equations is always kind of begging for the next big discovery. You know, what is the newest method to solve ever increasing differential equations? And so if you find yourself enjoying this, maybe you'll think about taking a diffie-q undergraduate course, in which case you probably would have seen about between a third and a half of it this term. If you're curious too, if you're wondering how I'm going to traverse through our textbook, my plan is to go through chapters 1 and 2 because there's some just fundamentals you need there. Then I'm going to go to chapter 4, with a few more fundamentals, but they get a little bit more interesting here. And then I'm going to jump and end our work here with chapter 7. So what I try and do in these elective courses is I like to give a necessary foundation, because you need a necessary foundation. And then I like to at least end with something juicy. So in linear algebra, that something juicy was vector spaces. In DiffyQs, we're going to land here in chapter 7 with something called a Laplace transform, which is pretty fantastic. But for us to get there, you do need a little bit taste of some of the basics. All right, so here is where I pulled out the notes, the outline I was going to be for today. Maybe you were able to print it out, and if you were, go ahead and grab it. And if you weren't, don't worry. You may just want to take down the information now and then transpose it onto a document, a blank document, when you are able to print. And if you still can't print, then I will happily give you a hard copy when I see you tomorrow, assuming that I myself can print. So, okay, let's begin. So what I'm going to do here is just lay down some the initial framework for our further study in DiffyQ. When we talk about solutions to differential equations, let's go back for a minute here. When I was talking about solutions to differential equations, I don't know where did I bloody hell, where did I go? Where did all my notes just go from a second ago? Goodness gracious. Here they are, okay? When we talk about a solution to a DiffyQ, so for example, this being a solution to a DiffyQ, or a specific solution to a differential equation, the criteria of the solution that is often glossed over is the requirement that the solution of the differential equation has to be differentiable over an interval. So the requirement of differentiability is often just forgotten about, because when you're solving a DiffyQ, we're so kind of intent on getting to the family of solutions that we forget to think about the fact that, well, that solution has to be differentiable. So let's take a look at this example. If you consider the differential equation dy dx equals negative 2x to the negative third, go ahead and solve this with me. We're going to get to here, aren't we? Okay, or if you prefer this, right? So this is the solution to the DiffyQ. Now, from back in the day, if I was asking you for the domain of this family of solutions, you'd probably say that the domain is going to be negative infinity to 0, and then 0 to positive infinity. Because at x equals 0, of course, this function doesn't exist. And if you were to think about this graphically, this function here has an asymptote at x equals 0. So nothing new and surprising in terms of domain. If you are, however, asked for the interval of definition, often called I, the interval of definition of a solution to a DiffyQ takes into context the fact that this is just not a freestanding function on its own. This function was arrived at by virtue of a differential equation. And because it is a solution to a differential equation, it is then subject to the requirement of differentiability. And if you think about it, the interval of definition of this, right, the interval of definition has to be an interval over which this function is in fact differentiable. So there are two intervals of definition here. One interval of definition is this one. The other interval of definition is this one. Now, in this case, one could argue that both of these intervals of definition are the same length, so to speak. Do you understand? Because we're going from negative infinity to 0 and 0 to positive infinity. They're the same length. In the event you have a differential equation, solutions have multiple intervals of definition, and those intervals of definition are of varying lengths. If a question asks you for the single interval of definition that is contextually appropriate for this question, you want to pick one of two things. You want to either pick the interval of definition that is longest, okay? Or in the case of a DiffyQ, where you are asked to narrow down your general solution to a specific solution, the interval of definition you want to pick is the one that includes the given point. So let's say, for example, you were given this question here. And not only were you told to solve this differential equation, but then you were also given this point. You also know that that y of 2 equals 7. Okay? Well, if y of 2 equals 7, then you know that 7 equals 1/4 plus c. C is going to equal 7 minus 1/4, which is 27/4, I think it is, which is 27/4. So at the end of the day, in a question like this, where you are given a particular point on the solution, I can find this single solution. Right? If the question was then asking me for the interval of definition for this solution to the DiffyQ, the interval that I'm going to want to pick is the interval that contains this given point. So I would say here that the interval of definition would be the interval of x from 0 to positive infinity. Okay? But the most important criteria here is when you're asked for the interval of definition, you don't just write these two down as a collective. Here, a question like this where you're not given a point, you would say, well, there are two intervals of definition, right? And if you are given a point, you would pick that interval that includes the point, or you would pick that interval that is longest, also if you were not given a point on the DiffyQ solution. Okay? All right, explicit solutions to differential equations are functions in terms of the independent variable only, or f of x equals 0. I'll talk about this part in a second. Explicit solutions to differential equations are what you spent most of your time doing in AP AB or AP BC calculus. So for example, in fact, I'll just use the example above. If you had dy dx equaling, what was that, did I say? Negative 2x to the negative third, and we get here, y equals 1/x² plus c. Do you see how this is an explicit solution, right? The explicit solution, because it's the solution is in terms of x only. All right. Now, notice here, I said explicit solutions can be expressed in the form f of x equals 0. What on earth am I talking about? Well, I'll tell you. So here, if I'm looking at this and I know that y, pardon me, I had to pause for a second. When I say you can express any explicit solution in this form, what I'm saying here is that when you have the explicit solution, f of x equals 1/x² plus c, it is possible to set this entire explicit solution. I can take this and set it equal to 0. I have the ability to set, right here, the dependent variable equal to 0. Okay? All right. Implicit solutions are functions in terms of the independent and dependent variables. And I'll again talk about this form in a second. Let me give you an example of a DiffyQ that would result in an implicit family of solutions. So go right ahead and let's take this. dy dx equals, oh dear, let's see, let's do negative xy. Okay, let's solve this differential equation by the method of separation of variables. In the course of doing this, we'll do kind of a comfortable review. Separation of variables involves you first separating the variable, hence the name. Then you want to integrate both sides. We take this c, this constant here includes the constants on both sides of the equation, right? Because when you integrate the left-hand side, you get a constant. When you integrate the right-hand side, you also get a constant. And I think that I may have given you a DiffyQ that's actually going to be explicitly solved, but that's all right. Let's just keep going. I'm going to exponentiate to base e, and I get y equals e to the negative x² over 2 plus c, which I know some of you remember from last year. What happens here is e raised to a power, and where the power is a sum, I can use properties of exponents and rewrite it this way, can't I? And e to the c is just a constant in and of itself. So what you've mostly seen before is the family of solutions is y equals k e to the negative x squared over 2. Here's your family of solutions, and I just messed you and me up because this gave us an explicit solution, not an implicit. How silly. Okay, let's do this. I think what I meant to do, no, I know what I meant to do is this, so bear with me, so sorry. Here we go, negative x over y. Well, you know what? Consider this just a practice of separation of variables. Let's go right ahead, and I'll meet you here when you finish. You get y dy equals negative x dx. Y squared over 2 equals negative x squared over 2 plus c. X squared over 2 plus y squared over 2 equals c. Why did I do that? Because I kind of saw what's happening here. X squared plus y squared equals some constant k. So here I separated the variables, I integrated, I collected x and y on both sides, and then I multiplied the equation by 2, right? But 2 times c is just going to be some constant k. And interestingly, you know what equation this is? It describes a circle. How funny. How funny. Okay, so really what happens at the end of the day is this is a family of solutions. Notice here, please. This is a family of solutions that is implicit because the family of solutions involves both the independent and the dependent variable. Now, what of this notation here? Well, what this means is an implicit solution to a Diffie obviously is not going to be just a function of x, because look at this statement here. If your solution's in terms of x and y, then obviously the solution is going to be a function of x and y. So what is my function of x and y? Well, watch what I do here. If I just do this, x squared plus y squared minus k equals 0, look what I'm looking at. This here is just a function of x and y, set equal to 0. That is it. That is it. All right, everyone good? Good, good, good. Okay, let's keep going. Oh, I write here, sometimes an implicit solution can be expressed as 2 distinct explicit solutions. For example, and you know what we can do, we might as well use our example right here. So in the example over here, if we have x squared plus y squared equals k, as luck would have it, this implicit solution, because of just the nature of the terms we have here, I could express it as 2 distinct explicit solutions. What that means is I could take this implicit solution and solve for y. And when I do so, I get this. Right? So here are my 2 explicit solutions. Now here is where I'm going to ask you a question, because we kind of gave away the surprise here. This is, after all, a circle, and this equation is the upper half of the circle. This is the lower half of the circle. What would you say is the domain of this? Let's just talk about this one here. What's the domain of this function of x? Okay, well, I think you'd argue and you'd say that the domain of this function of x is going to be from, oh, goodness, dear. The domain would be from negative k to positive k, right? Essentially the length of the radius, right? The radius kind of gives away the domain. However, the interval of definition of this explicit solution is an interval over which this solution is differentiable. And you'll remember, if you're talking about the upper half of a circle, there are 2 points here where the tangent line is going to be vertical. So those are 2 points of non-differentiability. So the interval of definition, notice the difference here. It's from negative k to k, not inclusive of the endpoints. All right? All right, here's something for you to try. Let's just kind of try and exercise just some thinking questions here. Given the differential equation xy double prime plus 2y prime equals 0, for what values of m will y equals x to the m be a solution to the differential equation? Go ahead and give it a shot and just, dive in and see what you can make of it, and then reply me for the answer. Okay, let's go through it. Well, the first thing we're doing here is looking at the differential equation, and you're looking at the solution and trying to manipulate this algebraically. A question like this, where you're given a differential equation, and then you're given a solution to a differential equation, and asked one of two things: either show that this is a solution, or kind of manipulate something about the solution to make this equation a solution to the diffie-q. These are very common, just introductory questions, okay, that ask you just to manipulate derivatives and diffie-q's. Well, the first thing I did here is I just did some kind of side work. Y equals x to the m is a just straight up power function. So here are my two derivatives. By substitution, I just have this right here. Here's y double. Here is y prime. And then just be careful here, right? X times x to the m minus 2. You add exponents, which then gives you this. At this point here, then I just looked at these two terms and I factored out a common factor, which is m times x to the m minus 1. And when you factor that out, here's what you're left with inside the parenthesis, which then simplifies here. And then you have three factors set equal to 0. And you're looking at what value of m will make each of these factors equals to 0. The one thing you're hopefully noting is that there is nothing that will make x to the m minus 1 equal to 0. Okay? Unless, of course, x is equal to 0, but that's not part of the question. So then, where are we? So you're asking yourself, what value of m will make this factored expression equal to 0? It's very clearly, I hope, m equals 0 or m equals -1. There we go. Okay? Little interesting note here. If you look at this differential equation, maybe you'll notice, actually, there's no reason why you would notice. So I'm telling you, if you look at this diffie-q for a second, do you see how if you're looking at this function of x, I mean, y equals 0 is f of x. Y equals 0 also satisfies this diffie-q, right? Because if y equals 0, every subsequent derivative of y equals 0 will also be 0. And that makes this diffie-q resolve into 0 plus 0 equals 0. And that this is pretty common in diffie-qs. Sometimes a diffie-q will have y equals 0 as a solution to the differential equation, but that trivial solution, and there's a reason why it's called trivial, that trivial solution doesn't manifest itself necessarily in the course of either solving the diffie-q outright or doing something like this, where you are looking at what values of m will y equals x to the m be a solution, for two reasons. One, y equals x to the m will never equal 0, because x raised to some power of 0 will never be 0 unless x is 0. But also, if I were to solve this longhand, which you don't know how to do yet, but you will soon, y equals 0 sometimes doesn't come up. So y equals 0 is often referred to as the trivial solution to the differential equation. In case you're wondering how a question regarding the trivial solution could come up on a test or quiz, it would have to be a pretty specific question. So a question like this could be, given the DE, for what values of m will y equals x then be a solution? And then part B would be, is the trivial solution a solution to this differential equation? It's just a matter of just inspection to see if y equals 0 is actually a solution. Okay. All right. Given the differential equation dy dx equals -x over y, where y of 0 equals 5, find the implicit solution to the differential equation. And now that I just think about it, this is no different than what we just did together when we talked about implicit solutions up above. So let's skip that for now, because it's literally an identical exercise. Okay. Yes. All right, here we go. Here's an interesting question. What kind of function satisfies the condition that the derivative equals 0 for all x values? Why don't you just go ahead and think about that for 2 seconds? If you're on your own, talk to yourself. I do it all the time. If you're with someone, then talk to them. But what kind of function satisfies the condition that the derivative, or dy dx, equals 0 for all x values? So for all x values in the domain of the function. Well, here's the answer. The answer is if y equals any constant. Right? So if y equals pi, or y equals 6, or y equals 7, this is true. The derivative equals 0 for all x values. Now here's a follow-up question. Based on your observation above, which of the differential equations below possesses constant solutions y equals k? I should say this. We should be able to do this just by inspection. Okay? If y equals k, which is called the constant solution. If y equals k is a constant solution to any of these differential equations, remember, what it means is that if y prime equals 0, which it would if y equals a constant, y prime equaling 0 should not turn any of these diffie-q's into any kind of apparent contradiction. So let's see what happens. I'll take a look at this one, for example. Well, if y equals k was a solution, that would mean y prime equals 0. And y squared and 2y would be a constant, right? So this would become 0 equals, it's going to be some constant squared plus 2 times some constant minus 3. Is it possible, right? Is it possible for 0 to ever equal the right-hand side? So the answer is obvious inspection says no, because if I think of the right-hand side, depending on the value of k, the constant, this right-hand side could be a positive constant, it could be a negative constant, in which case 0 doesn't equal a positive or negative constant, right? So in which case the constant solution would not be a viable solution. However, is it possible that k could be some value that would make this whole right-hand side equal to 0? Well, let's check. In other words, does this quadratic equation have a solution? I'm going to do a quick test of the discriminant of this quadratic, which is 4 plus 12, which equals 16. Okay, so very good. So right away, there are two solutions, there are two values of k for which this equation would be true. And those two values would be and 1. Good? All right. So answer to this question here is that in this differential equation, unless k were to equal negative 3r1, the constant solution is not a solution to this diffie-q. Okay? Or y equals k is not a solution to the diffie-q. All right. How about this one? What do you think? Y equals a constant. 0 plus 0 plus 6 times some constant equals 10, right? Well, unless k equals 10 over 6th, or 5/3, then y equals k is a solution, right? But if k does not equal 10/6, then y equals a constant is not a solution to the diffie-q. All right, you can go ahead and talk those two out. All right, let's see. Finally, are we almost done? Let me see, take a look here. Oh, this is it. Very good. Okay, so then here from your text, I think I pulled this, I don't remember what number it is. Number 22, I think. As I said above, in this very early stage here, the work with differential equations is often about just kind of making some observations and following up, or manipulating differential equations, or verifying solutions to a diffie-q. So this question says, verify that the one parameter family, this, and by the way, in case you're wondering what in the world does one parameter family mean, the one parameter refers to the fact that there's only one constant c involved in this implicit solution, okay? So verify that the one parameter family of solutions here is an implicit solution of the differential equation here. So let's see, there are several ways to go about it. My feeling is the easiest is to find dy dx of this equation implicitly and show that dy dx does in fact equal dy dx here. As I was just saying that, I was kind of eyeballing over here to see if by some chance this was a separable diffie-q, and it is not. So right now, is that right? Yeah, this is definitely not separable, is it? So right now, I would say that the most efficient way to go about this verification is to take d by dx of this equation and then solve for dy dx. Let's not forget how to do implicit differentiation. Go ahead and try it and then replay me for the answer. All right, kids, here we go. So d by dx right here. Watch your implicit differentiation, your dy dx's. I divided everything by 3. I collected dy dx terms on the same side of the equation, then factored dy dx out. Everyone understand? And then I divided by this, and this is where I am. And this is where I'm guessing some of you got here and said, what? That's not that. And you kind of had this emotional experience, right? And then you said, well, I'm noticing this is what I got. I have to make it look like that. There's no C here. And so here's where you go back and you say, what's C? Oh, C is just this, right? I just simplified. So C is this. And when you input C into C here, look what happens. Okay. And maybe you'll have another emotional reaction when you look at this, but maybe you will tell yourself, calm down, because this is not that bad. Right? This y's cancel here, the x's cancel here, which brings me here, right? And then once you're here, oh, look at the numerator and the denominator. We can get a common denominator in the numerator. Does that make sense? A common denominator in the numerator and a common denominator in the denominator. And we get this. And then we're going to do well, we can simplify now, look, because x cubed minus 3x cubed, 3y cubed minus y cubed, multiply by the reciprocal, the 3's cancel, and I believe this is this. Brava. All right, everybody, have a wonderful day with heat. Hopefully you are nice and warm and toasty. If you're not, keep drinking warm water. It's good for you and also good for your skin. I will post homework on the teacher page. Goodbye.